So, talking about how languages function, how grammars function within languages, how all of that intersects with how computer languages. Is that just the air ducts?
Yeah.
How that all works with how computer languages function in comparison to human languages, and how parsers work with interpreting grammars to produce a result. And then finally, I'll talk through how parsers are useful for application programming. So in my case, it's a gem that I wrote that uses a parser generator to evaluate mathematical equation strings in Ruby safely. So a caveat is that a lot of this is going to be high level, especially on the theory stuff. So you take a semester-long compilers course in a CS degree. If you want to actually understand compilers, you can get a PhD in just that. And you could also get a PhD in just linguistics. So there's a huge amount of depth that I'm going to gloss over or just omit for the sake of the presentation. The goal of it is to more give you kind of a high-level working knowledge related to parsers, and then more sort of practically how they can be useful for things other than like I'm writing a compiler for my language. So brief introduction to language. First, a few terms I'm going to kind of walk through. So there's a few distinctions that become relevant in literature related to parsers and grammars. The first one is the difference between natural languages and formal languages. So when we say natural languages, we mean things like English, French, Spanish that sort of evolves naturally, as the name implies, and they're used mostly by humans for communication with each other. That's also where natural language parsing, it's parsing natural languages, which is a hard and separate class of problem because of the ways that natural languages can be ambiguous, require context, things like that. On the other hand, there's formal languages, which are things like Ruby that are designed by people to solve a specific purpose or to express a specific thing. So Ruby is an example, XML would be an example, SQL, pretty much all programming languages. They generally have a very definitive and limited syntax where each word has specific meaning, and there usually aren't things that appear in human languages like idioms or turns of phrase or stuff like that that computers really don't care about. Lexical versus syntactical grammar. So lexing in general is the process of taking a string input and breaking it up into the words that make up the string. So what that means is finding the, if I was to lex an English sentence, Zach is a programmer, I would break that up into 4 tokens or words or sort of logical units. So Zach is a programmer. And then I could interpret those to figure out, what does the sentence mean? And that's where kind of the parsing part of it comes in. So lexing in general refers to the process of tokenizing a string into sort of logical tokens that can then be handled in some way, as opposed to just being a free-form string, where anything could be in it. So lexical grammar specifically describes the universe of valid words that could be used in a language. So in English, developer is a valid word, but those characters I matched is not. In Ruby, we have def or end or class are all valid words, but there's arrangements of symbols and things like that that you can do that Ruby won't know how to lex in the first place, much less get to parsing. So syntactical grammar operates kind of a level above lexical grammar, and it describes how words can be arranged to form statements or sentences. So in English, Zach as a programmer is a syntactically correct sentence, i.e. it takes valid words and then it also arranges them in an order that makes sense and actually says something. Banana, apple, pear is lexically valid because those are all words that exist, but it's not syntactically valid because it doesn't mean anything to put them together unless you need more potassium in your diet, I guess. In Ruby, there's also a lot of restrictions on valid token arrangements. So, if you have a def without an end, you'll get a syntax error in your code. If you have like multiple operators in a row, like 5 times plus divided by 2 or something, you'll get syntax errors. So there's restrictions on the combinations of tokens that can make sense, even if the tokens by themselves are still valid. Syntax versus semantics. So the syntax, or syntactical grammar, describes the form of what a valid statement looks like, but it doesn't necessarily guarantee that that statement conveys meaning or conveys the meaning it's intended to, just that it's structured correctly. So a famous example in linguistics is colorless green ideas sleep furiously. It's grammatically correct, like it has, you know, a noun and a verb and the pieces all go together the way English is supposed to, but it doesn't mean anything. And similarly, you can have things like John is a married bachelor, which sort of means something, but the thing it means is contradictory, so it certainly doesn't convey whatever meaning that it's intended to. Semantic analysis is kind of a level even above syntactic analysis, and it can provide some further guarantees that the meaning of the program is actually valid or matches what you wanted it to do. So type checking in strongly typed languages is an example of that, where you know, there's the lexical level, which is, are these valid words, like int abc equals 1. There's the syntactic level, which is like, does the sequence int abc equals 1 actually mean something, and you know, do those tokens make sense in that order? And then the semantic level is, you know, did 1 get assigned to an int, or are we trying to assign a string to an int? And then there's a semantic error that you might run into in, you know, Java, for example. This does actually happen in Ruby too, but it's much more under the scenes because of Ruby's duck typing. So if I say like a equals string ABC, and then I say a equals 1, Ruby will just figure that I wanted to change the variable from a string into an integer and just let me do that, which is a form of semantic analysis. It's just a very, you know, weak and permissive form that kind of just assumes the developer knew what they wanted to do. Whereas strongly typed languages have much stricter semantic analysis that says, you know, you can't put different types of variables into each other because that's probably a bug and, you know, you need to do better. So I mentioned sort of earlier the distinction between natural and formal languages. One of the biggest distinctions is the role of context and also of ambiguity in natural languages. And these are reasons why natural languages are poorly suited for computer programs and why we don't code like in English, for example. Context is information that helps you interpret the meaning of the language, but it's not strictly contained in the grammar. So it includes things like idioms. So if I say, what's up, you know, am I asking you what's going on, or am I asking what's above my head? The context might also, you know, inform that, because if I walk up to a friend and say, what's up, they would think I was asking them what was going on. But if I, like, you know, saw a sign that said danger overhead and I walked up to the foreman and said, what's up, well, I guess it might also interpret it that way. But there's other interpretations based on context. Another example is like, I'm sorry. So, you know, if you say something and I don't quite catch it and I say, I'm sorry, that is interpreted as, I didn't hear what you just said, please repeat it. But if you're at a funeral and I walk up to you and I say, I'm sorry, then you probably think, oh, he's expressing sympathy because my relative died or whatever. And there's also inflection as a part of context, because you notice when I was saying I'm sorry as in pardon me, it was like I'm sorry that goes up at the end, but if it's I'm sorry at a funeral, it's, you know, slower, lower tone and kind of more monotone. All of these are things that humans just naturally learn to process and to interpret, but it's things that are very hard for a computer to understand because, you know, they don't have 5 senses, they don't really understand inflection. It would be very weird to try to code with inflection and things like that. Ambiguity is also kind of a part of this, which is, you know, related to context, and that the context that you have helps you as a human to disambiguate confusing statements, but as a computer that doesn't have context, it's much harder to. So you can have words like bank that's like, you know, you can bank on it, like you can count on it, or I'm going to go to the bank and deposit my money or whatever. Computers are not nearly as good as sorting out the distinctions between those words based on their context. So if there's one person you know in kind of linguistics or I guess theories of grammar and things like that, it should be Noam Chomsky, in my opinion, because he's one of the most, I think one of the most influential people that's ever lived in terms of like his impact on his field. He basically defined linguistics, and, you know, all of the scholarship that happened in linguistics for like a couple of decades was around a lot of his work that challenged previous notions around how grammar works and things like that. So he had a theory of universal grammar, which may or may not actually be correct, because most of the people after him have spent time saying that he wasn't correct and there's actually other things. But it's a really interesting theory. It says that basically there's something that's in our genetics or that's biologically evolved that makes us understand things about grammar. And so his example for this, or his warrant for this, I guess, is that across languages, when you have parents that are teaching their kids, or kids that are learning from their parents how to speak the language, the parents don't give the kids the full vocabulary that the kid actually ends up using, and they certainly don't give them all the valid combinations of things that they could end up saying. But the kid still manages to put the pieces together and start forming structures of their own that go beyond what the parent has actually told them or what they've actually seen modeled. And so his theory was that this means that there must be something that's universal about grammar in sort of the human psyche that lets us understand language and take limited input and use that to construct how the language works. Most of the attacks on this theory have been things like, well, there's this tribe in the Amazon that don't seem to exhibit this behavior, so it can't be like universal to humans, and it gets really esoteric really quickly. But definitely like very influential in terms of all that. He also wrote a bunch of political and philosophical works, and for computer science, the biggest contribution he made was something called the Chomsky hierarchy of formal grammars. So the Chomsky hierarchy divides languages into 4 groups, or grammars to be specific, into 4 groups: recursively enumerable, context-sensitive, context-free, and regular. So they're what's the word? Inclusive of each other. So everything that you could express with a regular language, you could also express with a context-free language. But there are things in a context-free language that you can't express in a regular language. An example of this, so with this, you can kind of think of that boundary as the distinction between a parser versus like a regex that you would write within Ruby or whatever. Regexes can do a lot of stuff, but they can't do, they can sort of do recursion based on the language and how they're implemented. Regexes can't do things like counting, so if you want to write a regex that says match strings that have some number of zeros and then an equal number of ones, regexes can't do that because there's no way in a regex to say like count the left side and count the right side and make the 2 things match. Counting can be done, or counting, it's not strictly counting, it's more like of how recursion works, but it can be done in context-free languages. So context, I guess I'll start at the top. So the type 0 recursively enumerable languages are all languages that can be recognized by a Turing machine, which basically means any language that you could possibly describe a logical route to understanding or interpreting. And if it's, if you don't have rules for how the language works at all, then it's like not a language. So it's sort of like by definition of being a formal grammar, it's recursively enumerable. Context-sensitive languages include most languages that are human or natural languages that human-derived, because again, humans have context that influences how we interpret things, and so if you can express that in your language, then you can get to most of the languages that humans speak. Context-free languages are basically programming languages. There are some edge cases in which programming languages aren't technically context-free, but by and large they are context-free, which means that each thing within the language can only have one possible meaning in the area or in the location that it's at within the code. There's not ambiguity that requires you to understand the speaker or the location or the setting or things like that. And again, that's sort of the principle of the hierarchy, right? Is that you can, like, humans could talk in Ruby if we wanted to. You can express everything in Ruby in English, but you can't express everything in a context-sensitive language, in a context-free language, because you wouldn't be able to understand the context. So how does this all connect to kind of languages and actual programming code, etc.? So a couple more terms. So a Lexer, I sort of alluded to earlier, but specifically a Lexer is a program that takes text input and converts it into a series of tokens. So if I had like parentheses 2 minus 3 times 5, I would turn that into left paren, num, minus op, num, right paren, etc. This is the part where you determine whether the string you've been given has valid words in the first place, because the parser operates on finding meaning in combination of words. So if not everything is a word at all, then it would never be able to parse correctly. So it's sort of a first step to normalizing the text into a series of tokens that match what the language understands. And so this is the level at which you would have, it would catch Ruby code that you write that's not a valid word, like the example I had earlier with just a couple of like greater than symbols or whatever, something that's not even a valid word in Ruby. The Lexer's output is then given to the parser, which is a second program that reads in the series of tokens, and it creates a syntax tree, or sort of a logical representation of the syntactic relationship between the tokens. And so invalid syntactical grammar is caught by the parser. So for example, in Ruby, if it reads in a def word, and then you have your method or whatever, but then there's no end at the end of it, then it's not going to be able to parse it because something's not going to match up later on in the parser. So that's where you would get syntax error, expected to find an end but found an end of file instead, or whatever that error that you get if you forget to do that. There's a lot of different parser implementations, and also a ton of computer science around compiler theory is based on like different parser implementations. So Some of them make it easier to express certain kinds of grammars. Some of them are more performant for certain languages, but not necessarily other languages. And this is all also super low level and esoteric and very boring if you're not like hugely into compiler theory. So this is a lot of the area that I'm kind of glossing over for the sake of brevity. Fundamentally though, most parsers use a stack of tokens, which is a stack in the computer science sense. So they consume input tokens from the lexer, and based on the rules of the grammar they've been coded with, they can either shift, which means they push a new token down onto the stack, or they reduce, which means they take the top token of the stack and the input token, combine them in some way, and then push that thing onto the stack, or whatever the case may be. So if you can think of like a Ruby program where you're defining a method like def ABC, and then has something inside and then end. So I would encounter the def, and then I would say, okay, this is the start of the method, push that onto the stack because I have to see what's left in the method. Next I see ABC, okay, this must be the name of the method because it matches that, so I push that onto the stack. Then the stuff inside the method, all gets processed, popped off of the stack, etc. Then I get to the end, and at some point I'll have the only token left is an end, hopefully, and then I'll have the only thing left on my stack is a def, and then I say, okay, def end, I've got the complete method, that's done being parsed, and so that's kind of the syntax tree for the method. Or if I forget to put the end in my code or whatever, then it would get to a point where there's still a def on the stack, but there's no more input tokens, and so it's confused because the stack isn't empty, so there's something left over, but it doesn't know how to resolve it because you forgot to put the end there, or whatever. There's also some parsers also do look ahead, which means that instead of looking at just the very next token, they can look at more additional tokens in what's coming up in the string that came from the lexer. And so that can make it easy to express certain grammatical rules, but it also it makes the parser less performant if you care about that in your context. So programming languages are all context-free-ish. All of them are something very close to context-free. You can understand their syntax just by looking at what the token is and where you are in the stack, or more broadly speaking, it always means the same thing. There's no ambiguity. It doesn't matter where you are in the code or what kind of person you are or anything else. A few of them get some help. So context-free grammars actually can't express white space sensitive languages or like give meaning to white space. I don't fully understand why this is the case, to be honest, but I read on Stack Overflow that it's true, so it's got to be. But there are other examples also within C internals with things like type defs or macros, in which the lexer kind of does some extra processing to help the parser understand where it's at or what these tokens mean or whatever, which technically makes them not context-free because in Python, for example, the context of whether you're 6 or 8 spaces deep or whatever matters. But for our intents and purposes, they're basically context-free in that they follow the same rules as other languages. There's just some sort of extra processing you need to do.
They'd be like, they would be referring to like if we have like a even column of rows to indicate like where the words are arranged into a data table. Maybe that's something that the lecturer doesn't perceive as that when the information is organized in a neat column of rows. That'd be what they're talking about.
Yeah, I think the problem is mostly around, so you could, part of it is how do you figure out what is like a word of white space? So is it 2 spaces or is it 4 spaces? I think a lot of white space languages let you do what you want, like they don't make you indent every 2 spaces or whatever, but then that makes it impossible to parse because you don't know, like is 6 spaces like 3 2-space indents or 2 3-space indents or whatever. And there's other stuff too, but that's all.
When you got 20 character columns and this is, some of the words almost fill the column, but other words do not.
Yeah. So putting it all together, for the vast majority of programming languages, the computer interprets code in a few steps. So the lexer takes the string that's the raw file input and converts it into a series of tokens that have logical meaning. The parser consumes all of the tokens and it converts them into a syntax tree that represents the logic of the program. And then the syntax tree gets evaluated, which at runtime means we send a series of commands to the computer that are ultimately assembly, like put this here, move this here, jump, etc. And programming languages are generally context-free, which is why it's easy for computers to understand them. So why should you care? There's a couple of reasons why this is useful information to have. So it's nice to have a sense of what goes on under the hood and what your syntax errors mean or what's actually causing them on a lower level. And it helps you code better maybe if you know what a syntax error is or what the terminology that it's telling you. It's always like loosely based in the thing that it's trying to do to parse it, like was expecting an end, found an end of line. Parsers are also an extremely powerful tool at the application layer though for evaluating inputs and extracting sort of structure or instructions or whatever the case may be from a user provided string. So this is the problem that I had when I implemented the gem that I'm going to talk about in a little bit. AHA has scorecard functionality where you can score your features using a custom equation, and then you can fill in metric values for each feature for that equation. So like in the settings, I would say the score of my feature should be benefit minus 2 times cost plus 3 times value, or whatever I felt like typing in there. And then for each feature, I could pull up that scorecard and say, okay, this feature has 2 benefit and 3 cost and 5 value. And then it works out that makes 11 based on the equation that I had. So if you sub in the values the user gives you, you end up with a string that's like the equation they gave you, and then you sub in the values, so you end up with 2 minus 2 times 3 plus 3 times 5. But it could be any arbitrary math equation, and we don't want to limit you, based on what we can figure out how to parse or whatever. So we can't plug it into eval because the user could put all sorts of nasty things in there, like semicolon, hack the server or whatever. We could try to scrub the input, but that's really hard to do, and it's really scary to get it wrong if you don't implement it correctly. So that seems like a not great solution. We can't really solve it with regex very well either. So we could maybe write like a recursive regular expression that solves all of math. But this would be super painful and complicated, and it would be a super huge regex that probably nobody could maintain and wouldn't be great. I can't give up. This is an important feature. My boss will be unhappy. But it turns out that basic arithmetic can be expressed as a context-free grammar. And doing it like this and using a parser to solve the problem has, pretty much solves the issues that I described. So it's very safe. We're not evaling anything. If you put nasty input in there, it's just not going to parse because it's not valid math. And even if it did parse, you would just get some other error like string times 5 doesn't work or whatever. It's relatively easy to avoid bugs as well because the parser does all the heavy lifting, and the application code only has to solve simple problems like, I've got a syntax tree where 3 is on the left and 5 is on the right, and it's a multiplication. How do I get the result of these 2 things? Rather than having to say, okay, I've got a regex and let me count all the matches and try to make the parentheses line up and all that sort of stuff. So specifically parser generators to the rescue, not just parsers. So every language has a parser generator, and when I say a parser generator, I mean something where you write a grammar that describes your language as a file, and then it takes that grammar and generates a parser, which is a class in Ruby or whatever equivalent in C, etc. And then you can give that parser your text string and then have it parse and give you back the result or whatever. So every language has them pretty much. So C and C++ have Lex and Yak. Ruby got creative and named theirs Rex and Rack. And there's other ones in Ruby like Treetop, which is the one I used for this problem, and I'll talk about in a minute. Parser generators are very solid, so they're built on decades of scholarship. They're basically what's used to actually compile languages in general, and it's hard to find bugs in them because they're so well developed. They are kind of at the point where if you look at any one of them, you'll see there's no commits in 5 years or something, but that's because they just have stopped having bugs. On the flip side, it's very hard to roll your own parser, so there's a lot of bugs and edge cases. You have to deal with recursion. You have to make sure you handle edge cases around tokenization. What if there's like weird cases on the boundaries of tokens or just different things like that that you get into. And there's also a lot of like theory to kind of understand about how recursion works and some of this stuff that they just do for you. And you end up writing a ton more code because you have to write all the code to like split apart the string, interpret it, create a syntax tree, etc., and then figure out how to evaluate that. So this is my gem, EQN, that uses the Treetop parser generator to evaluate mathematical equation strings. And actually, yeah, that works. I'm just going to walk through the code a little bit and kind of show how this sort of thing works. as a practical example. So the way it looks is just a Ruby gem. You can install it.
Keep up the size of it.
Oh, you mean you can't read 5-point font? Is that better? One more. Cool. So it works. It's just a gem you can install, and then you can call calculator.calc, and you can pass it a string, which is a math equation, and then it solves the equation and gives you back the solution. You can also check if it is a valid math equation in the first place, and you can use variables in your equation if you want to, which makes it easier to use user-provided input without having to do interpolation. So if you want to do 5 times value and then give it the value or whatever. So the grammar that is given to the parser generator lives in this eqn.treetop. EQN or treetop, one of the things that's nice about it is that its grammars have a relatively Ruby-like syntax, which makes it easy, at least for me as a Rubyist, to understand. So Rex and Rack have a weird, low-level-ish syntax that feels more like assembly or something than Ruby. And there's some other things that are easier to express with treetop. A grammar basically kind of has two parts, which are rules and then terminals. So terminals are symbols that can't be reduced anymore, like they are what they are, like a plus sign, for example. You don't need to do any parsing with a plus sign, it just is a plus sign and that's what it means. Rules are how terminals can be combined in some way to create broader expressions. So I might have a rule that says, generally speaking, number plus sign number is an expression that exists in my language, and I know what to do if given, a node that has two numbers with a plus sign because I can add them together. So rules are generally done in this kind of weird recursive fashion that's a little hard to get your head around. So the basic idea here is that for each rule you give it what makes up that rule, and then you also give it the name of a Ruby class, and so then whenever it matches this rule in the language or in the text that it's parsing, it creates a new instance of this Ruby class that has the contents of the thing. So let me see if I can find a simpler example at the bottom. If I have a float, for example, so there's here's an example. If I have an exponent sort of thing, so that's like if I have 10e5 or whatever that math notation is, I would have an exponent and then possibly a space between it depending on what I decide to do, and then sign float, which would be the thing that's after the exponent sign. I can't remember the name of that part of the thing. So if I have 10e 3.5, this would be the 3.5. So then it creates an exponent class that has those three things in it, which then the exponent class can get evaluated to figure out the solution to that. So what you end up getting out of this is a tree of these sort of nodes, where you have one node at the very top level that's a comparison or expression or whatever. And then each of those nodes have children that can be other nodes, and then they can have children that are other nodes. So that's sort of the syntax tree concept. And then you can have a value method on the top level node that will figure out the value of its children nodes, and then however it needs to put them together. And then the children nodes get their value called, so they look to their children to see how they get put together, and so on and so forth. And let me show an example to make this maybe a little easier to understand and start drawing. So if I had just 3 plus, plus sign 2, this might get parsed out as something where I have a node that's a add operation node, and then its children are 3, which is a node, but it's just a terminal because you can't break that down anymore. And then 2, which also is a terminal. This node class will have a value method, and so it would invoke the values of its 2 children, which are just 3 and 2. They would just return themselves. And then it would say, okay, my 2 children are 3 and 2, and I'm a plus node, so let me return 3 plus 2, and that's 5. And then you can sort of see how this would be recursive, right? Because if I had like 3 plus 2 plus 3, then I might have another add node up here, and its children, it's a terrible plus sign. It's hard to draw with a trackpad. Are this node, and then 3. And so when it gets its value called, because it's the top level node now, it would say, okay, what's the value of my children? I've got 3, and then I've got whatever this value turns out to be, so then we recurse down, figure out this value is 5. Okay, I've got 3 plus 5, let me add those together, and then return the result upwards. So that's kind of the simple case. The reason why all of this stuff is as complex as it is to get the rules of, or the order of operations to be correct. So this is easy enough when it's all pluses, but when you have like 3 plus 2 times 5 minus 4 or something, you have to have a way to work out that the times needs to happen first, and then I guess it doesn't matter, the plus or minus or whatever, but you know, you might have nodes that are not necessarily in the order of the way that they actually need to be evaluated. Yeah.
Did you make this parser, or did it already exist?
I wrote this grammar, and then the parser generator takes this grammar and turns that into a Ruby class where I can feed it a string, and it gives me back a tree of nodes that are parsed or that match my grammar.
Is there a library of already made grammars somewhere?
I don't know of one. There's, if you look for like treetop examples or whatever, I think treetop on their README has like some libraries that were made with treetop or whatever that would have example grammars. But it's sort of each grammar tends to be specific to each domain or problem it's solving, so it's not a thing where I mean, this one is more reusable than a lot of them because it's just math, which is maybe a common use case, but a lot of them are very specific to some query language someone wants to write for their server or whatever the case may be, so they end up not being all that like generally useful.
Yeah, I was gonna say, I don't know, a long time ago I did something very similar to what you have here, but not in Ruby. And yeah, I think what you have here is very general purpose and can be used for a lot of business cases.
Yeah.
If you need a business person to sort of write rules against some set of like known variables for whatever, whatever business function they have. I think this is probably a good example if you're looking for one.
So the way we deal with order of operations is by having kind of nesting of the rules in a way that makes it turn out right. So I have an expression which is the kind of the top level. The reason why comparation is above expression is because a comparation is like a greater than or less than or equal to comparison. And so it's kind of the very top level in that it can compare two expressions. But then an expression is the top level thing that you might think of as like a group of numbers or whatever. So an expression has a multitive, which a multitive I'll go down to in a second, and then it can have possibly an add subgroup. So a multitive is kind of a grouping of something down at the next level, which is where the order of operations comes in, because the only thing the expression can parse is something plus or minus another thing. And so then the plus or minus ends up being at the very top level, which means that the multiplication has to get done down a level and its value calculated before you get up to finding the value of the expression where the two things might get added together. Hopefully that makes sense. It's recursive and like hard to explain. So then multitive, exponents are even higher precedence than multiplication. So if I have like, 5 times 3 to the 2 or whatever, I have to figure out the 3 to the 2 first, and then I have to do the 5 times whatever that outcome was. And so it's the same sort of principle where I have the exponentiative rule to get that as kind of one group. And then I might have that multiplied or divided by something, which forces it to get the value of the exponent or the power operation, and then take that, and if there was a times or a divided by, then take the result and do it with that. The exponentiative group has, or exponentiative, not group, as an operand and then it might have a space and a power group, where a power group is like to the 2 or whatever. And then an operand is either a number, which is just 1, 2, 3, whatever, and that's a terminal or at the bottom level, or it could be a parentheses group if I have like parentheses something to the something, or it could be a function, which is a more advanced feature that I won't get into. So what this actually means is that if you just parse like 3 plus 2, for example, it'll start out with comparation. It'll say, okay, I'm looking for expression, and then possibly like a greater than, less than symbol in another expression. I only have the expression. I don't have the comparation thing because I'm just parsing 3 plus 2. There's no greater than, less than, etc. So the expression, multitive, let me parse that. Multitive, there's no multiplication happening, so let's go down. Exponentiative, there's no explanation happening. So the number is the number 3, the first thing in the 3 plus 2, is an exponentiative, which gets passed up to a multitive, which gets passed up to an expression. So then I say, okay, the multitive is 3. Now I have this plus 2 that I can put on the end of it and then turn that into 5. If it was like 3 times 2 plus 5, the 3 times 2 would get evaluated a level down to get turned into a 6 or whatever, so the order of operation stays correct. Hopefully that makes sense.
So this file is arranged in order of operations, and like highest precedence at the top?
Yeah, kind of. So it will, treetop in general will match rules in order, like it'll take the first rule that it matches, which is why you want to have this kind of order so that you like match the correct things. And then the sort of recursion is also used to enforce the order of operations. So like multitive to exponentiative to number, the kind of levels you have to walk through to make sure that things are getting combined at the correct level. So the way that code actually shakes out is there's a bunch of nodes that it'll produce that are in a tree with each other. So look at this first. So when I call calc or calculate, parser is something that gets given to me by treetop, so it takes in my grammar and it gives me this parser class that has a parse method. This parser will have a top level node that's like an expression or whatever, so I can call value on that node because I want to know what the value of this entire tree is, because that's going to be whatever my equation reduces to, and I'll pass down any variables that I have that I might need to insert into the equation. So the nodes, say I have an expression at the top level, so it has a value. Every node has elements, which is an array of its children, basically, or the things that make up that node. So for an expression, it's going to have like, it could be like a 3 plus 2, or it could be like a 3 minus 1, or it could just be like a 3. So the base is I'll figure out the value of the first part of the expression by calling value, which then recurses down to whatever that happens to be. In this case, maybe just a 3. I have to aggressively consume the left associative operators, which is how, so subtraction comes before addition, which I didn't know until I did this, but if you have like 7 minus 5 minus 3, you have to do 7 minus 5 and then minus 3 from that instead of the other way around. And then if there's, so if we're out of nodes and we've terminated, then we just return the 3 because that means there wasn't like a plus or minus or whatever. Otherwise, I need to apply like so this is where if it was like 3 plus 1 or something, I would take the 3 and then I would send it the operator, which is plus, and then I would send it the value of the other side of the thing. So let's see. Terminal, this one might be relatively simple. So these are just the nodes for things that are like the lowest level of thing that can't be combined in any way. So I have operators, which can be a left associative op or a right associative op, and that's based on what the grammar created as the class for it. So the grammar will say, like, what did this match? Division is left associative, subtraction is left associative, multiplication and addition are right associative. So that's the one that it'll create based on that. the value of it. So in my math notation, you express exponents as like 3 caret 2 or whatever. But in Ruby, you have to do exponents as like 3 star star 2. That's how you do exponentiation in Ruby for whatever weird reason. So if this is a node where it's a like caret, then the thing I have to send is actually star star, and then I would be doing, you know, number.send star star comma other number. Otherwise, if it's a plus or a minus or a times or a divided by, I can just convert it into a symbol, because that's also the thing I need to send in Ruby to get the result of this. Digits, it's like a group of numbers. The basic case is just, you know, take the numbers and convert it to a float. So if I had like a 1, 2, 3 times 1, 2, 3, the 1, 2, 3 would just be a string as it comes out of the parser, but I know that that has to just be numbers, so I can just call .2f to get the number I can do operations on. The decimal value is how to work with like 0.123 times something. So if this is a decimal, then I have to do that. What else we have? Is that interesting? Anyway, hopefully you kind of broadly get the sense of how this works, in that it takes the grammar, reads in the string, divides up the tokens based on that into a syntax tree. Tokens are all Ruby nodes. They all have a value method that figures out what the value of that specific node is, and then you reduce them all up and you get one final value out of it, which is what the calculator then returns. So, where's my slides are very small. There we go. So I wrote this. I originally tried to use a different project called Dentaku. That's a gem that does basically the same thing. And the problem that I had with it is that this guy kind of home built his Lexer and parser. So he just wrote a bunch of Ruby that like lexes out all of the mathematical tokens, and then a parser that figures out how all the equations go together and that sort of thing. But I kept on running into bugs with his approach. So there was a problem with like a unary minus, which is like 2 times minus 3, which is minus 6 or whatever. But if you're writing your own parser, that's hard to figure out. It's like, it looks like 2, like you might get a syntax error because you don't realize the times can go right before a minus in that context or whatever. So I had like bugs like that, and I fixed a couple of them, and then I decided it was worth it just to write my own. And it also ends up being a huge amount less code. So mine has 818 lines of code, and the other one has 3,300 lines of code. Just because, you know, all I have is like my grammar, and then I have nodes that are the different kinds of operations that can happen in math and how to solve them, which is not that much code. Whereas, you know, for the other way, you have to add a bunch of code to lex everything out and then to parse it all and figure out how it goes together in the first place. Not to crap on that guy's project. He put a huge amount of work into it, and it, like, you know, I think anyone like doing open source or whatever is doing the community a good, even if I don't personally use their project. Just as a way of comparison, it's good to use a parser generator when you can instead, or not when you can, but it's good to use a parser generator in general instead of writing your own parser and running into the issues that'll cause you. And that's all I have. Any questions? Any of that make sense? Not make sense?
Can we see it in action?
Oh, like the calculator?
Yeah, I want to see it in AHA.
Oh, sure.
We can huddle around. If you want to pull up your laptop, and we can just huddle around.
Yeah, I can just log into like a test account on your laptop.
Give me AHA superpowers.
Did you get any pushback for making this open source?
No.
Because I'm going to guess that some development had to happen on company time to move this thing forward.
Yeah. So things like that, we go here. Things like that, like we don't have any problem open sourcing, like when they're useful, and you know, especially like this where it's easy to extract.
Yeah, awesome.
If it's something that's a lot closer to like the core competency, like code for roadmaps or something, that would be a different story. This is a test account where I created like a crap ton of features because I was stress testing something, so it's going to be a little slower than usual. But so I have this feature scorecard. for my features, which is the same one that I used as a demo on my
Mhm.
slide. So I have my equation, which is benefit minus 2 times cost plus 3 times value, and I can say, okay, benefit is 3 and cost is 2, the value is 7, so that gives me my score. Or I can type in these, stuff like that. And then that gives you a way to kind of at least try to be objective about scoring your features based on how they're gonna affect the business.
Where do you set the equation for your account for this
So
project
it's
or whatever?
in
it is?
the settings, I actually don't think
That real-time score we saw, is that actually going through that code, or is there like a JavaScript facsimile?
Yeah, it's just going through, there's just a slim backend or Rails endpoint that makes a network call. It says these are the score facts, which score facts are like the values for the individual metrics, and then it just responds, score
Mhm.
whatever, and then if I change it, it'll make another call and give me the new score. So there's a settings area where you can type in the scorecard equation, which is the thing that I showed in the slide, but my test account doesn't have any access to like the account settings of my test account, or at least the specific test user.
Yeah.
This is the only one where I don't have the password in 1Password, so I can't show that part, but that's what it does.
I wanted to see how you were handling like invalid grammars and stuff like that.
Yeah, so so I mentioned that there's a valid like question mark method on EQN. So it works. The place where you enter your equation works similar to the front end there, where you type something in and the field has a red or a green outline,
Yeah.
and it says like equation valid or invalid equation. And every time you change the equation, just debounced, it hits up the server and says, is this equation valid? And then it just plugs it into that, says true or false, and then we show them the input based on that, and don't let them save if they have an invalid equation.
Yeah. Cool. Sweet.
Cool.
I
Yeah.
heard that. Oh, good.
I'm thinking there should be some way or program to take a grammar that's like we're just in so-called Bacchus and Noah form, and get a parsing code out of that. Is that?
Yeah, so if you use Rex and Rack, which are the kind of not quite built-in, but basically built-in parser generator and Lexer for Ruby, those take a form that's very similar to Bacchus Noor form. Let me find example.
So instead of writing that code, if we write out the grammar we want in Bacchus Noor form, then it can auto-generate the code.
Yeah, so the equivalent is, so this is actually kind of a equation solver, although I think it's a little bit simpler. And this is what rules would look like in Rack, which is not exactly Bacchus Noor form, but it's kind of simple. So it's saying the X can produce this, or it can produce this, or it can produce this. And that's the equivalent for Rack of the treetop file I have here. The treetop is just a nicer syntax because it looks like Ruby, whereas this is like, it's still Ruby, but it's less pretty Ruby, I guess.
I can't see that from here.
Oh, yeah, I guess that would probably help. So this is how you would write a rule in Rack, and then, no idea how to spell that. Bacchus Noor form. There we go. That's a good picture. Bacchus Noor form looks like this. So you say there's a left side, and then it can produce this right side, or this right side, or this right side. You can see how this is basically the same as this. The X can produce this right side, or this right side, etc. Just this is Ruby.
Yeah, you kind of see how it's similar to what you built.
Yeah. So this is like the X can be this or this, and then mine is the expression can be this and possibly this. It's just a little nicer syntax, I think. And it's also easier to code a calculator with, because with Treetop you can get basically multiple elements into your node. So you can have like the expression node that has 3 plus 3, and then it's easy to say, okay, I have these nodes, I need to add them and return it. Whereas with rack, it's a stricter recursive descent parser, which makes it so you can only have 2 nodes or values or whatever that you're working with at a given time, which makes it trickier to, like, you have to write a lot more code to put the pieces together, basically.
So is that, to test this, do you just have like dozens of different equations that you run through?
Yeah, that is actually pretty much what the tests look like. So I have full test coverage. So I wrote a RSpec shared example that I use for all of these, and then I just have a bunch of different things. So correctly evaluates 1 plus 1 is supposed to be 2, minus 3 plus 1 is supposed to be minus 4. And then I've got different cases, so I tried to cover all of them, like decimals and unary minus times unary minus, and all of that. That, and then there's some for comparation and some for everything else, functions, etc.
Cool.
Turned out to be the easiest way to test it, especially just because if you think you have a bug, you can just add a test case and
Yep.
then, you know, either you know exactly what you need to fix, or best case you have another test.
Now, I was gonna say, like, you started to show a little bit of code that handled the variables that you could feed into these, but then sort of skipped over that.
Oh yeah.
I don't know if there's a reason.
Because
for
it
that.
doesn't work, Joel.
No, I was just trying to, it's like, there's the level that's do the numbers, and then there's the level that's numbers and functions and variables, so I was just trying to keep it high level. But the way that works though is, so you call the calc method, you give it the equation, and then the second thing is a hash of variables, so it was like, 5 plus ABC, comma, ABC colon 3 or whatever. And then the variables just get passed down throughout the tree, and then there's a type of terminal that is a variable, which is this. And so that's what gets generated by the grammar whenever it's just something that's A to Z that we don't otherwise recognize as a thing, then that has to be a variable name, or maybe it's a parse error, but that's how it's parsed. And so then when we get
Can't
down,
use emoji in your variable name.
you cannot. You can send me a PR to add that there. So the vars get passed down through each level of the node until they get down to the variable terminal, and then the variable just says, okay, my value is, look in the hash of vars for whatever I am, and that must be my value. And
Or yell.
check if it's actually there, and check if it's a number, but otherwise that's what the value is. And then every other value method, like the expression, value, vars, sends it down to all of the value children that it calls, and etc., so that it gets down through the tree to the level of the variable.
Can you go back to the errors that were thrown for a second?
Variable
You
ones?
were just, wherever you were.
Yeah.
Not that it matters, but did you do any speed tests on this, just versus like maybe like a math function on it, like run 10,000 ops or something and see what the
Not really, no. It's going to be an order of magnitude slower, just because it's parse the string and then do the calculation instead of just do the calculation.
Yeah.
And I'm sure that also like Ruby itself has optimizations for like 3 plus 5 that I don't have or whatever. But I didn't really have a need for it to be like blazing fast though, because it's just like one web request, and it's like milliseconds of time or whatever, so it's like fast enough.
Yeah, and obviously completely different use case.
Yeah, for sure. The other guy who did the Ntaku, I think, has some benchmarks of his.
It's like just slow.
Oh yeah, he has that, and he also has, that's another reason not to roll your own, is he had to like implement an AST cache to cache the syntax tree of the parser to avoid it like being slow regenerating the syntax tree every time or whatever, which Treetop has done a lot of those abstractions at the level of creating the parser in the first place, so you don't have to mess with it. and then there's like a crap ton of code that's all these different things. Police, blah blah, parser. This is 300 lines, and then you have to like manually figure out all of the different possible error cases, and work out how do I make sure brackets are balanced, parentheses are balanced, groupings, parentheses, blah blah blah. Which again, not crapping on his work, just like this is why it's a better approach to use a parser generator, because it has it's a solved problem for most of the things that you run into.
Okay, you learned a lot.
Yeah.
Oh
definitely.
yeah, they did.
Are parser generators ever used in DSLs?
It's a good question. So in Ruby, I don't really think so, largely because Ruby itself is pretty powerful. So you can just define methods in Ruby for whatever you want in your DSL. They are used, well, I hope they are used in things like, if you use Jira, they have JQL, which is Jira Query Language. And so it's a query language in Jira that you can use to say, like, select the issues with this name, or it's quasi-SQL, but for Jira, basically. That's the kind of thing that you use a parser generator, or at least, hopefully they used a parser generator. I don't know for sure, because I don't know what their source code looks like. But that tends to be the more of the case for it, though. So DSLs are more kind of within the language itself, where you can just define Ruby methods that are whatever you want to express with your DSL. Parsers are more for either parsing structured user input, or parsing structured files of some kind where the file has a certain format and you need to get the information out of it. So like XML parsers, for example, either are or should be parser generators, or JSON parsers, or things like that.
Thanks.
Yeah.
So EQN looks like it's got the capabilities of defining functions within the equations. Is that true, or did I just not understand what I was seeing earlier?
So it has limited capabilities. It has a couple of predefined functions that you can use in your EQNs. So you could do rounds, parentheses, number, or whatever else, and
So
then it
they're
would evaluate that.
predefined.
Yeah.
I was gonna ask you how found that customers needed to define their own functions
Yeah.
to do this. So okay.
No, that is one thing I think Dentaku has. I think it lets you define your own functions. Yeah, custom functions. So I don't have that. So if you need custom functions, then go with this, I
I
guess.
think
But-
You can
sounds
pass.
dangerous.
You got this. You just start passing lambdas in as your variables.
Yeah, that's also the thing is I don't know what exactly the use case is, because any function that you would want to let the user define is just a shorthand for some math string. But who's typing paragraph length math string such that they need to define a function instead of just copy pasting the string twice or something if they need the thing.